So the first video had solved the second order reducible differential equation using one method where we assumed that the independent variable is missing. Now we can assume that the dependent variable is missing because it is, and solve it a different way. So we're going to start with the exact same helper variable we used last time. So v equals y prime, which equals to dy dx. And we'll see why this is important later. So v prime equals y double prime. We also have to remember that v equals dv dx. And this is important because dv dx, when we can multiply by 1 to produce the same without changing its value. So instead of multiplying by 1, we're actually going to multiply by dv dx. We're going to multiply it by dy over dy. And then we're going to shift all these d around to produce dv dy times dy dx. And remember, dy dx is equal to v. So this is actually equal to v dy v dv dy. So now our y is kind of a pseudo-independent variable because we're differentiating with respect to it. From here, we're going to substitute v in for y prime and v dv dy in for y double prime. So our new equation looks something like this. V times dv dy plus v equals 0. So actually at this point we can divide everything by v and say that dv dy plus 1 equals 0. And now it's variable separable. We have dv plus dy equals 0. From here we have dv minus d equals negative dy. So we can actually just integrate both sides and we get v equals negative y. Now remember we had set v was equal to y prime. So we have y prime equals negative y. Oh, I forgot the constant. Plus constant. Plus constant. Y prime equals negative y. To solve for y prime, we can also separate this, I think. No, we can't. This is not a separable equation. So we have y prime plus y equals c. This is actually a linear first order that can be solved using the form e to the power of integral of px dx times y equals the integral of qx e to the integral of px dx dx. Makes that x a bit more clear. So looking at our equation, we know that p of x is equal to 1 and q of x is equal to c. So we can rewrite all of this as e to the integral of 1 is just x, e to the x times y equals some constant. Qx is a constant, so we can factor that out. E to the x dx. Then we can integrate again. So y times e to the x equals c times e to the x dx plus, oops, didn't need another dx, e to the x plus some other constant k. And then we can divide the whole equation by k to find that y equals c plus k over ex. And that is the final form, that is the final solution of this differential equation, assuming when we use the method such that we take the dependent variable as to be missing. Now we can compare these answers actually. We see that y equals negative k e to the negative x plus c1. And we see that y equals c plus k times, this is just e to the negative x. So we find that from both solutions, we found the same, we had to obtain the same solution using both methods.